Preparing for Embedded Systems Engineer Interview Questions and Answers interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What is the difference between a microcontroller and a microprocessor? A microcontroller integrates the CPU, memory, timers, communication interfaces, and often analog peripherals on one chip. A microprocessor usually provides mainly the CPU and depends on external memory and supporting hardware. I would choose a microcontroller for deterministic, low-power control tasks, such as motor control or sensor monitoring. I would choose a microprocessor when the product needs high computation, rich operating systems, or complex user interfaces. The decision depends on performance, cost, power, and software requirements. While answering, compare CPU architecture, integrated peripherals, memory, power consumption, operating systems, cost, real-time behavior, and typical applications such as appliances, automotive controllers, and smartphones. Question 2. How would you design a reliable interrupt-driven system? I keep interrupt service routines short and deterministic. The ISR captures essential data, clears the hardware condition, and signals a task or sets a flag for deferred processing. I assign priorities based on urgency and protect shared state using atomic operations or carefully bounded critical sections. For example, a UART ISR can place bytes into a ring buffer while a task parses packets. I also measure latency and overflow behavior under worst-case interrupt load instead of relying on nominal timing. Make sure to cover interrupt priorities, minimal ISR execution, shared data protection, latency, nested interrupts, deferred processing, volatile variables, debouncing, and measuring worst-case response time with hardware tools. Question 3. What is the purpose of volatile in embedded C? The volatile qualifier tells the compiler that a value can change outside the current code flow, so every access must be performed as written. I use it for memory-mapped registers, flags modified by interrupts, and status locations updated by DMA or hardware. However, volatile does not make operations atomic and does not provide mutual exclusion or memory ordering. For shared counters or multi-threaded data, I still need atomic instructions, locks, or carefully designed critical sections. In your answer, explain compiler optimization, memory-mapped registers, interrupt shared variables, hardware updated memory, limitations of volatile, and why atomicity or synchronization still requires separate mechanisms. Question 4. How do you prevent and diagnose race conditions in firmware? I first identify every shared resource and document which contexts access it, tasks, interrupts, DMA, or hardware. Then I define ownership and protect multi-step updates with atomic operations, mutexes, or bounded critical sections. I avoid taking blocking locks inside interrupts and establish a consistent lock order. To diagnose failures, I add timestamped tracing, assertions, watchdog breadcrumbs, and stress tests that vary timing. Reproducing a race often requires increasing interrupt frequency or deliberately inserting scheduling delays. Be sure to mention shared resources, interrupt and task concurrency, atomic operations, mutexes, critical sections, ownership rules, lock ordering, static analysis, tracing, and stress testing under timing variation. Question 5. What is a real-time operating system, and when would you use one? An RTOS provides scheduling and synchronization services designed to help tasks meet timing deadlines. I would use one when firmware has multiple concurrent activities, such as communications, control loops, logging, and diagnostics, that are difficult to manage with a superloop. I would define task priorities, bound execution times, and measure worst-case latency. An RTOS adds memory and scheduling overhead, so for a small, simple product with a few periodic operations, a well-structured superloop may be safer and easier to verify. Focus on deterministic scheduling, deadlines, task states, priorities, preemption, interrupt handling, synchronization, latency, resource usage, and when a superloop is simpler and more appropriate. Question 6. How would you choose task priorities in an RTOS? I prioritize tasks according to deadline urgency and the consequences of missing deadlines, not simply perceived importance. A fast control loop usually outranks telemetry or logging. I estimate execution time, period, blocking duration, and interrupt interference, then perform schedulability analysis. I also use priority inheritance or ceiling protocols for shared resources to limit inversion. Finally, I verify the design with runtime measurements, stack monitoring, and overload tests, because theoretical priorities are only useful when implementation timing matches assumptions. Cover deadline urgency, execution time, blocking behavior, rate monotonic reasoning, priority inversion, interrupt priorities, starvation, schedulability analysis, and validating assumptions through runtime measurements. Question 7. Explain how DMA works and when you would use it. DMA allows a peripheral to transfer data directly to or from memory without the CPU moving every word. I would use it for high-rate UART, SPI, ADC, audio, or network traffic, where polling would waste processing time. I configure source and destination addresses, transfer length, direction, and completion events, often with circular or double buffers. On cached processors, I must handle cache maintenance and ownership carefully. I also validate alignment, buffer lifetime, and error handling before enabling the channel. In your answer, discuss direct memory access, peripheral transfers, CPU offloading, buffers, descriptors, cache coherency, ownership, completion interrupts, alignment, and data corruption risks. Question 8. How would you design a bootloader with secure and reliable firmware updates? I would separate the immutable bootloader from application images and use 2 image slots when flash permits. The bootloader verifies a signed image, checks its version and integrity, then switches the active slot only after installation completes successfully. A power failure must leave a known good image bootable, so metadata needs redundancy and atomic state transitions. I would also enforce rollback protection, protect signing keys operationally, and use a watchdog recovery path. Encryption may protect confidentiality, but signatures are essential for authenticity. Make sure to cover image validation, cryptographic signatures, rollback protection, power loss recovery, versioning, memory layout, watchdog behavior, fail-safe slots, transport integrity, and key management. Question 9. What are common causes of stack overflow in embedded systems, and how do you detect them? Stack overflow commonly comes from recursion, large automatic buffers, deep call chains, excessive interrupt nesting, or undersized RTOS task stacks. I avoid recursion and large locals, then estimate usage with static analysis and runtime high watermark checks. Filling unused stack with a known pattern helps measure peak consumption, while guard regions or MPU protection can catch corruption earlier. I also record fault context, stack pointers, and task identity in the crash handler. Sizing should include realistic worst-case paths, not average behavior. Discuss deep call chains, recursion, large local arrays, task stack sizing, interrupts, stack painting, guard regions, high watermarks, static analysis, fault handlers, and production monitoring. Question 10. How do you debug a hard fault or memory fault on a microcontroller? I begin by preserving the fault status registers and the stacked CPU context, especially the program counter, link register, and stack pointer. I map the faulting address to the linker map and disassembly, then inspect pointer values, alignment, permissions, and recent stack usage. Common causes include invalid memory access, corrupted return addresses, executing erased flash, and unaligned operations. I add assertions, MPU protection, and watch points where useful. A reliable crash record is more valuable than simply resetting the device. Be sure to mention fault registers, stacked CPU context, program counter, link register, stack pointer, map files, disassembly, corrupted pointers, alignment, and reproducing the triggering sequence. Question 11. How would you implement a debounced mechanical button? Mechanical contacts can change state several times before settling, so I do not treat one transition as a valid event. A simple solution samples the input periodically and accepts a new state only after it remains unchanged for a defined debounce interval. I then compare the stable state with the previous stable state to generate one press or release event. Polling is often predictable and inexpensive. An interrupt can wake the processor but still requires software debouncing. I choose the interval from measured hardware behavior. Focus on contact bounce, sampling interval, stable state duration, edge detection, interrupt versus polling trade-offs, active low wiring, EMI resilience, and avoiding repeated event generation. Question 12. Compare polling, interrupts, and DMA for peripheral communication. Polling is simple and predictable for slow peripherals, but it consumes CPU time and can miss events if the loop is delayed. Interrupts improve responsiveness by notifying software only when service is needed, making them suitable for moderate data rates. DMA is best for sustained, high-volume transfers because hardware moves data while the CPU performs other work. I select the method based on throughput, latency, power, and complexity. For a short status register read, DMA would add unnecessary overhead. In your answer, compare CPU utilization, latency, throughput, complexity, determinism, buffer management, low power behavior, and appropriate use cases for each transfer method. Question 13. How do you design a communication protocol for an embedded product? I define an unambiguous frame format with synchronization, version, type, length, payload, and CRC fields. The receiver uses a state machine so malformed bytes cannot permanently desynchronize parsing. I add sequence numbers, acknowledgements, bounded retries, and timeouts when reliable delivery matters. Versioning allows older devices to reject unsupported features safely. I also specify maximum lengths, rate limits, and behavior for invalid commands. Testing should include corruption, truncation, duplication, reordering, and hostile input, not only valid frames. Cover framing, synchronization, payload length, addressing, sequence numbers, checksums or CRC, timeouts, retries, versioning, flow control, malformed input handling, and compatibility strategy. Question 14. What is the difference between UART, SPI, and I2C? UART is typically asynchronous point-to-point communication using transmit and receive lines, with no shared clock. SPI uses a clock, data lines, and chip select signals, offering high speed and full duplex but requiring more wiring. I2C uses two shared open drain lines with device addresses, making it efficient for multiple low-speed peripherals. I choose SPI for displays or fast sensors, I2C for many configuration devices, and UART for debug or simple external links. Electrical levels, cable length, and error handling also influence the choice. Make sure to compare wiring, duplex behavior, addressing, speed, topology, clocking, electrical requirements, arbitration, error detection, and practical device selection criteria. Question 15. How would you reduce power consumption in a battery-powered embedded system? I start by measuring current in every operating state rather than guessing. Then I reduce active time through event-driven software, lower clock frequencies when performance allows, disable unused peripherals, and batch sensor or radio activity. I select the deepest sleep mode that preserves required wake sources and retention. Power domains can disconnect inactive components, but wake latency and state restoration must be handled. I validate battery life with realistic workloads, temperature, and aging, because datasheet current alone rarely represents product behavior. Discuss clock scaling, sleep modes, peripheral gating, duty cycling, interrupt wake-up, sensor scheduling, leakage, power domains, measurement techniques, and preserving timing or responsiveness requirements. Question 16. What is a watchdog timer, and how should it be used correctly? A watchdog resets the system when software stops making progress within an expected interval. I avoid feeding it from one always running timer task, because that can mask failures elsewhere. Instead, each critical task reports health, and a supervisor refreshes the watchdog only when all required activities meet their deadlines. I choose the timeout longer than legitimate worst-case operations but short enough for safe recovery. After reset, firmware records the watchdog cause and relevant breadcrumbs so recurring faults can be diagnosed. Be sure to cover independent recovery, timeout selection, failure detection, supervised tasks, refresh ownership, windowed watchdogs, reset diagnosis, and why indiscriminate periodic feeding can hide software defects. Question 17. How do you handle endianness, alignment, and portability in embedded C? I never assume a wire format matches the processor's native representation. I use fixed-width integer types and explicit serialization functions that shift and mask bytes according to the protocol's defined endianness. For alignment, I avoid casting arbitrary byte buffers to wider pointers and use safe copies or byte-wise assembly. Packed structures can create unaligned accesses and compiler-dependent layouts, so I use them cautiously. Compiler warnings, static analysis, and tests on different architectures help expose portability defects early. In your answer, mention byte order, unaligned access, serialization, fixed-width types, masks, compiler behavior, packed structures, undefined behavior, and testing across architectures. Question 18. How would you test embedded firmware effectively? I use layered testing. Host-based unit tests validate logic quickly with mocks for hardware dependencies, while integration tests exercise drivers and real peripherals. Hardware-in-the-loop tests verify timing, electrical behavior, resets, and recovery paths. I include boundary values, corrupted packets, sensor disconnects, low voltage, watchdog resets, and power interruption during updates. Coverage is useful, but it does not replace requirements-based tests. Automated regression on representative boards catches toolchain, configuration, and hardware integration issues before release. Focus on unit, integration, hardware in the loop, fault injection, boundary testing, timing analysis, code coverage, mocking, regression automation, and validating behavior under power, temperature, and communication faults. Question 19. Describe a robust motor control firmware architecture. I would run the control loop from a hardware timer at a fixed frequency, synchronize ADC sampling with PWM, and calculate duty cycles from validated feedback. Fast protection, such as overcurrent and overvoltage shutdown, should operate in hardware or the highest priority path. A state machine manages startup, running, stopping, and fault recovery, while communications remain outside the timing critical loop. I would characterize worst-case execution time, calibrate sensors, and test abnormal loads. Determinism and safe failure are more important than feature quantity. Cover control loop timing, sensor feedback, PWM generation, ADC synchronization, protection limits, state machines, fault handling, calibration, real-time constraints, and separation of control from communication tasks. Question 20. How would you investigate an intermittent field failure that cannot be reproduced in the lab? I would first define the failure precisely: frequency, affected versions, operating conditions, and recovery behavior. I would add non-volatile fault records containing reset causes, timestamps, sensor values, task state, and software identifiers, while respecting memory endurance and privacy. Then I would correlate reports with temperature, supply quality, vibration, and usage patterns. Controlled stress testing can reproduce the suspected trigger. I preserve failed units, compare good and bad traces, and make one change at a time so evidence remains interpretable. Make sure to cover failure characterization, telemetry, reset and fault logs, environmental correlation, controlled experiments, version tracking, instrumentation, statistical analysis, and preserving customer hardware and evidence. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.